Hi, everyone. Uh, for this lecture, we are going to just briefly review the functional groups and families that I discussed last time. And then we're going to delve into one of my favorite aspects of organic chemistry, the naming of the molecular compounds that make up organic chemistry. And it's a very specific system that was devised intentionally so that scientists can communicate to one another about a particular molecule that they're studying, and they can do that in a universal way by naming it with this standard system so that when they're talking about some molecule, scientists elsewhere know exactly what that molecule is made of and how it's arranged. And so we'll get into that today, and that'll be the bulk of this lecture. Okay, so without further ado, let's get started. So let's see where we last left off. We were talking about these families or these functional groups. These families are made up of their functional groups, right? And I'll just go through these quickly because I went through them much more slowly last time. But an alkane is only going to be carbon and hydrogens with single bonds. Alkenes, carbon-carbon double bond. Alkyne, carbon-carbon triple bond. And then you have aromatic compounds that have this hexane ring with alternating double bonds. Alkyl halides are going to be a carbon that's bound to a halogen like fluorine, chlorine, bromine, or iodine. Alcohols are going to be a carbon bound to an oxygen that is then bound to a hydrogen, or this hydroxyl group. Ether is a carbon-oxygen-carbon group. So an oxygen with two carbons on either side. And an amine is going to be a carbon that's bound to a nitrogen. Then we get into these more complex, what we call carbonyl groups up top. An aldehyde is a carbon-oxygen double bond and a hydrogen, okay? So just, again, focus on the things that are in red, all right? So on all of these, you're gonna have carbons to the left, but what makes an aldehyde is a carbon that has a double bond with an oxygen and then another bond with a hydrogen. Ketones are going to be, again, carbon-oxygen double bond, but instead of having a hydrogen, it has a carbon in place of it. Carboxylic acid, again, carbon-oxygen double bond with an alcohol group or a hydroxyl group at the end instead of a carbon for ketone or hydrogen for aldehyde. An anhydride here is kind of like an ether, right? It's a COC, right? So an oxygen sandwiched by two carbons. The only difference is that those carbons on either side of the oxygen have double bonds with additional oxygens. An ester is a lot like an anhydride, except instead of both carbons having a double bond to an oxygen, there's just one carbon that has a double bond to an oxygen. Amides or amides are like amines, only that carbon that's bound to the nitrogen also has a carbon-oxygen double bond, okay? Thiols are carbons bound to a sulfur that is also bound to a hydrogen. A disulfide is two sulfur groups bound, or two sulfur atoms bound each to carbons. So the sulfurs are sandwiched in between these carbons. And a sulfide group is just going to be one sulfur. sandwiched between carbons. Here's another way of looking at it. I like to try and provide more than one graphic for these things because some are better for certain people than others. And so if this one works for you, then you can look over this instead. It also has some additional groups, like epoxide based on this ring structure that's being formed. So it's like an ether, only it's got a ring. What else? Arine, these other isocyanates. So there's a few other groups in there that weren't mentioned in the other table because they're a little bit less common. So let's practice, shall we? Why don't you pause it here and use these tables to see if you can determine which of the organic compounds belong to which family do these compounds belong to. All right, so pause it here and then we'll go over it. Okay, so I don't know why I stopped sharing my screen, but all right. So what do we have for A? Let's get my little annotating tool. What do we have for A? Well, we have this double bond here, right? So the family that's going to belong to is alkene, right? It's an alkene because it has a double bond. For B, we just have carbons and hydrogens, but oh, look here. Here's this hydroxyl group. So that's going to be an alcohol. For C, look here. We have a 6-carbon ring with alternating double bonds. That must be an aromatic compound. Here we have a carbon with a double bond to an oxygen, and then a carbon to the left and a carbon to the right. That is a ketone. Here we have a carbon-oxygen double bond and a nitrogen. So that's got to be amide. But look here, it also has a carbon bound to a nitrogen there. That's an amine, right? The reason that this is an amine and this is an amide is that this doesn't have a double bond to an oxygen, and this, I don't know if you can see my little pencil, but this does, right? So that has 2 functional groups, 2 different kind of families. And then here we have, here's another one with 2, right? What's that? That's an aromatic ring. And it's also got carbon, sulfur, sulfur, carbon. So it's an aromatic and it's a disulfide functional group that make up that molecule. So as you can see, many organic compounds are going to have more than one functional group, right? As they get more complex, just by nature, they will have more than one. So here's another test. We have lactic acid, methyl methacrylate, and phenylalanine. See if you can find all the different functional groups in these 3. Okay, so pause it if you want and review the tables and see what you come up with. Okay, so for A, what do we have? Well, we have, let's go, let me do my annotation. We have a carbon with a double bond to an oxygen and then an OH group. So that is a carboxylic acid, if you look at that table, right? We also have a carbon that's bound to a hydroxyl group. So it's an alcohol. So we have an alcohol and a carboxylic acid as the functional groups here. Okay. For B, we have a double bond between two carbons. So that's going to be an alkene, right? And then we have this carbon that's bound to an oxygen and another carbon. So that's not an ether, right? Because it's got this double bond to an oxygen. It's not an anhydride because this one doesn't also have a double bond, right? So it must be an ester, right? Carbon, double bond, oxygen in the middle, and then a carbon that is not double bound to an oxygen, ester. And then finally, we have an aromatic ring here, right? 6 carbon ring, alternating double bonds. What else do we have? Well, we have another carboxylic acid group. And we have a carbon bound to just a nitrogen. So that's an amine group. And because it has an amine group here, and because it has a carboxylic acid group here, that's why this happens to be an amino acid. Yes. An amino acid has an amino group, an amine group, and a carboxylic acid group. And that's why it's called amino acid, which we'll get into next week when we talk about biochem. Okay. So this was brought up last Thursday briefly by Brian during Journal Club, the idea of isomers. So if you don't know what an isomer is, it's a compound that has the same molecular formula. So the same number of, in this example, carbons and hydrogens, but arranged differently. So the atoms themselves have different arrangements. Okay, and so if we look at this formula here, it's essentially what, C5H12, right? We can arrange those carbons in different ways, right? We can put them all together, 1, 2, 3, 4, 5 in a chain, right? We can have one branch off here, right? So we have 4 here, and then the 5th one coming off here. Or we could have, this kind of T-shaped structure, okay? We still have 1, 2, 3, 4, 5 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. All of these have the same number of carbons, the same number of hydrogens, but have very different molecular structures based on how those carbons are arranged. And therefore, they will likewise have different properties associated with them. Oh, you're gonna make me go back. Okay. Also, the more carbons in the molecule, obviously, you're going to have more isomers, right? If you have methane here, let's change the color because it's a red background. If you have methane, that methane only has 1 carbon, right? So you can't have any isomers. There's no way to, do carbon by itself in any different way. So there's just going to be one form of that, right? It's going to look like this. A carbon, that's a terrible C, but So, all right, carbon and 4 hydrogens. There's really no other way to arrange that, right? Same with ethane, right? Ethane is 2 carbons. So carbon, carbon, and then 6 hydrogens that go around it. Okay, you know, same right here, 3 hydrogens there too. There's no other way to do this. You can't you know, rearrange this. So there's no other isomers for ethane either. And same with propane, right? It's not until you get to 4 carbons that you can then start putting those carbons elsewhere. Okay, so and interestingly, well, I guess not interestingly, but expectedly, the number of isomers, you know, greatly increases as you go up. So going from 4 carbons to 5 carbons, you get 1 additional isomer. But then when you get to 6, you jump up to 2. When you get to 7 carbons, you have 9. And by the time you're up to 9 carbons, you have 35 different combinations that you can do with those carbons to make 35 different isomers. Okay, so that's isomers for the molecule. Turns out that functional groups can also have isomers. Okay, so if we have a formula of C2H6O, we could write that out like this, right? 1 carbon, 2 carbons, so there's C2, 1, 2, 3, 4, 5, 6 oxygens, and 1 hydrogen. I'm flip that. 6 hydrogens and 1 oxygen. Okay. Well, what is that? That's an alcohol, right? Because of this OH group. So that would be ethyl alcohol or ethanol. We can take those same number of carbons and hydrogens and oxygens and arrange it differently. Instead of putting the oxygen on the outside, we sandwich the oxygen here between the 2 carbons. And we get what? What's an oxygen with 2 carbons on either side that doesn't have a double bond to an oxygen? That's an ether. And what we'll get into shortly, it's dimethyl ether because it's an ether with a methyl group here and a methyl group here. Okay, so that's dimethyl because there are 2 methyl groups. You know, if we had something like this, where there's a methyl group here, and instead of this being a methyl group, this was an ethyl group, right? Then this would be different. This would be an ethyl methyl ether, right? And we'll get into that naming system very shortly. Okay, that's clear. That stuff. I also talked about how the different ways that we have to write these formulas out. So you can have a complete structural formula where you write out all the atoms and all the bonds that are present. Okay. Of course, that's going to be the most information, but if you're in organic chemistry and you're writing about it, I mean, that's a lot of work. So it's easier to do these alternative versions, like a condensed formula where you don't write this out as what would this be? This would, you could say this is C, whoops, undo. You could say this is C3H8, right? But that doesn't tell you how it's grouped, right? So a condensed structural formula still spaces it out and tells you that, well, you have a methyl group here and a methyl group here, and then this CH2 group in the middle. The skeletal structure really abbreviates things. And so essentially this is a carbon, and this is a carbon, and this is a carbon. And it hides all the hydrogens. The hydrogens are assumed, right? So this carbon would have a hydrogen here, and a hydrogen here. And then of course there would be 3 hydrogens on this side, so that the carbons have 4 bonds, right? Because carbons like to have 4 bonds. Okay, so all this stuff, little tiny h, it's hard to write on my trackpad. So all this stuff is implied in this line structure. Okay, 3 carbons. Now, if let's say we wrote it like this, where now this becomes an alcohol. Now we've shortened it to 2 carbons. We're saying that there's a carbon here, and then 3 hydrogens. There's a carbon here with 2 hydrogens, and then this is no longer a carbon. This is showing that it's a bond between the carbon and the oxygen, and that would be ethanol. You can also write a condensed structural formula by putting the bonds in there too, but I mean, it's not as common. This is by far more common. I think the top condensed structural formula version. All right, so that's a review of that, and let's try it. Okay, so for each formula, draw the complete, the condensed, and the skeletal structures. So pause it here, review this stuff here, and see what you can come up with for each of these. And I will see. I'm gonna stop sharing. I'm gonna pause it. Okay, so hopefully that worked and made sense. But if not, we're gonna go over it right now and see what we come up with, see if we get the same answers. Okay, so it was complete, condensed, and skeletal. So the complete for C2H6 is, well, C2, right? So there, H6. 1, 2, 3, 4, 5, 6. Okay, condensed would be CH3, CH3, right? Representing this carbon with 3 hydrogens and this carbon with 3 hydrogens. And then the skeletal structure will just be that. Pretty simple, right? Because again, on each side of the line is a carbon, and then right, the hydrogens. But we like to be lazy and not have to write all that stuff out, so we just write a line. Okay. C4 complete, that would be 1, 2, 3, 4. And let's do the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. Works. That's the complete. What would the condensed be? Well, we have a CH3 here, so CH3, CH2, CH2, another CH2, CH2, and then finally a CH3, so CH3. If you add those up, you know, 1 carbon, 2 carbon, 3 carbon, 4, so C4. 3 hydrogens plus 2 is 5, plus 2 is 7, plus 3 is 10. So it all adds up. And now the skeletal is 1, 2, 3, 4. You got to do zigzag so that you can, differentiate the lines. If you just drew one long line, how would you know how many carbons is in there, right? So there's a carbon here, carbon here, carbon here, carbon here. And 3 hydrogens here, 2 hydrogens here, 2 hydrogens here, 3 hydrogens on the end. Okay. So 1, 2, 3, 4. 1, 2, 3, 4. That's it. That's all we got to do. Let's go back to sharing. That's it. So that was that. Simple, right? Not too bad. But what if it's like this? We have the ball and stick structures instead of just written out in the formula. Okay, so pause here. Try to do this one, and we'll compare our answers. Or I guess you'll compare your answers. Okay. All right, so actually, I decided I want to go back to the slide and just kind of walk you through this. Let's figure this out, okay? So how many carbons do we have here? We have 1, 2, 3, 4. So that is what? C4. And then how many carbons or hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, that's tricky because it doesn't show you the 10th one, but that should be H10. Interesting. Yeah, trying to trick you. But right, because this carbon has to have 4 bonds. It's only showing 3, but there must be one going through the screen, so behind that carbon. So that's C4H10. What's this one? This next one is 1 carbon, 2, 3, 4, 5, 6. Okay, so that is C6, C6H. Now, how many H's are there? 1, 2, 3, 4, 5, 6, 7, 8. There's got to be another one on there. 9. 10, 11, 12, 13, 14. C6H14. Now, maybe you're noticing a trend here where if you have 4 carbons and there are no double bonds or other groups, it's just carbons and hydrogens. If you doubled 4, you'd get 8. And 8 plus 2 is 10. So if you doubled 6 here, right? So we doubled the 4 and we added 2, and that gives us 10. If we double the 6, that's 12 plus 2, 14. Okay, so that's a handy little thing to just automatically know how many hydrogens you have based on the number of carbons. So let's see if it holds true for the next one. We have 1, 2, 3, 4, 5, 6, 7. So that's C7. How many hydrogens should we have based on that? We should have 16, right? 7 times 2 is 14 plus 2 is 16. So that's one, I wonder, right? 1, 2, 3, 4, 5. There's got to be one here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sure enough. Okay. So I'm going to write this down on my board. I got a C4H10. We've got a C6H14 and a C7H16. And what are they asking for? They're asking for the condensed structure for the molecules below. Okay. So for this, now we got to see kind of how they're arranged. Let me get rid of, let's get rid of this stuff. I guess maybe I won't write on my board. I think I can just do this on the screen. Okay, so what do we have? We have a C3. We have a CH. 1, 2, 3, 4. Yeah. And we have a CH3 here. And then we have a C, this has to be a CH3 there. So if we were going to write the condensed formula, we could write it as CH3, CH, CH3, CH3. And that is the condensed structure. So let's get a different color. Okay. So this CH3 is referring to this part. Let's get fancy, do a bunch of different. This CH is referring to this. The other CH3 is referring to this one or this one. It doesn't really matter at that point. They're interchangeable. And then this CH3, that. Okay, that's the condensed structure. We could also write it if we were, doing the skeletal structure. That would be, what did I say? 1, 2, 3, 4. Same thing. 1, 2, 3. Whoop. Undo. 1, 2, 3, 4. And then what did I say? This one was C6, H14. Okay, well, let's see what we got. We've got CH3. We have a CH again. We have a CH3, another a CH2, CH2, and a CH3. Okay, so let's write that out. I said a CH3, a CH, just a CH for this other one, CH3, CH2, CH2, CH3. Okay. Come on, how do I, ooh, I don't know what's going on. Okay. I was hoping I could move that. Let's see, come on. I just want to move it out of the way a little bit. Oh. Well, anyway, I can't seem to move my text box, but that's what it's going to be. So the first CH3 is, so this is the, oh, come on, draw. So this is the first, oh man, technical difficulty. So this is the first CH3. This is the CH2. This is the CH3. This is the other CH2, CH2, CH3. For this one, this was C7H16. So, right, there's a CH3, there's a CH2, here's a CH, here's a CH2, CH3, CH2, and CH3. So that would be CH3, CH2, CH, CH2, CH3, CH2, CH3. Okay, hopefully that makes sense. Explaining it in this way without kind of writing it on the board, but that's how we would draw the condensed structures for these molecules. Okay, so that brings us now into actually naming these things. Okay. And like I said at the very beginning, we have to be very stringent and particular in how we name these chemicals because they do get complicated. And depending on where that hydroxyl group is or that nitrogen is, changes the molecule, right? And so if we don't number it the right direction, if we put our functional groups in, if we number them in different ways, it really just changes the perception of what that molecule potentially is. So the International Union of Pure and Applied Chemistry, or IUPAC, has devised this three-part system that consists of a prefix, a parent, and a suffix. So the prefix is going to be the location of the functional groups and other what we call substituents. Okay, so things that are tacked on to that molecule. The parent is going to be what is the number of carbons that represent the longest continual chain. Okay, so when we start looking at these different molecules, you can look at them and see which has the most carbons in that given chain, which I'll go into in just a little bit. That's what's going to make up the parent. So whether it's a hexane or a methane or a butane, it's going to be based on that chain. And then the suffix is what family it belongs to. So does it belong to a carboxylic acid, or does it belong to an alcohol family, or does it belong to an anhydride family, that kind of thing. So this is the three-part system, and this is how we name all these organic compounds. And this is why, you read the back of a shampoo bottle that has a bunch of or anything that has a bunch of ingredients, and you see all these really long, drawn-out names. That's where this comes from. Okay. And so again, to review, if you have one carbon, that's meth. If you have two carbons, it's eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is none. And 10 is dec. So if we're talking about alkanes, it's going to be methane, ethane, propane, butane, etc. And if you're going to take organic chemistry, it'd be easiest for you to just kind of memorize this lineage. Okay, so just get it to where you can rapid fire shoot it off: meth, eth, prop, bute, pent, hex, hept, oct, none, dec. Okay, it'll make your life easier, trust me. So with that in mind, draw the alkane with the formula C3H8, and then name the molecule, and then do the same for C4H10. Okay, I don't think I'll have you pause it, and I mean, you can pause it if you want, but I think I'm just gonna go straight into this and see if I can help you with it, because we haven't really done any naming, so I don't expect you to be able to do it right off the bat. So let me write this down. We got C3H8. Again, following that rule, right? 3 times 2 is 6 plus 2 is 8. and then C4H10. Draw the alkane and then name the molecule. Let's see here. So what would that look like? It would be 3 carbons, right? 1, 2, 3, and 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 3 carbons is what? Eth, meth, prop. So propane. C4 very similar. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we call 4? Eth, meth, prop, bute. So this would be butane. That's it. Now it gets more complicated from there. This is the simplest versions of the molecules that we'll name in this lecture. But if you get that, we can just expand on it and make it even more complicated and fun. When we talk about these groups, these methanes and ethanes and propanes and butanes, when they are, again, these substituents, right? When in the first part of the naming system, so not the longest chain, but more of a substituent, we refer to them as alkyl groups. Okay, so think of it as alkane with a hydrogen removed, so alkyl. And we do that by, we drop the ane suffix and add an il, a YL. So methane minus 1 hydrogen becomes methyl, right? Okay, right here. So CH3 is not methane, CH4 is methane. CH3 is methyl. Likewise, CH2CH3, right? This first carbon has lost one of its hydrogens so that it can, essentially, so this combined to some other part of another molecule. Now it's going to be an ethyl group. Ethane becomes ethyl. Okay. And this will make more sense why I'm talking about this in just a minute. But, you know, essentially we have methane by itself. If we wanted to tack that methane onto some other molecule, which is done in with our DNA with methylation, you're just tacking on methanes, or, you know, essentially methyls groups onto you know, as an epigenetic marker to express genes, then yeah. Sorry, I don't know why I'm losing track. Maybe because it's late. You put a methyl group onto different molecules that it's no longer a methane, it's a methyl. Okay, and you can add ethyl groups as well. Okay, it's no longer ethane, it's ethyl. And here are some common alkyl groups. Of course, we have, oh, did I skip something? Yeah. So remember we said that propane can have doesn't have really necessarily uh, structural isomers, but we can have it attach differently to, we can have that alkyl group attach differently to a molecule, okay, based on which carbon is attaching. So we have propane here, right? And now we're going to take off one of the hydrogens. So if we take off this hydrogen right here on the end of this carbon, now this carbon has the availability to bind to something else, and we call it a propyl group, right? It's an alkyl group, so it's propyl. But we could also take off a different hydrogen. We could take off a hydrogen from the middle carbon. And if that's the case, now this area, or this carbon, is going to bind to the molecule. So it binds here instead of on one of the ends. And so we refer to that as isopropyl. Okay. And that's how we can differentiate between which carbon is attached to the rest of the molecule, the longest chain. For instance, if this was attached to a hydroxyl group, now that would be isopropanol or isopropyl alcohol, right? Because the hydroxyl group or the alcohol group is attached to the center carbon in the middle. If this was the hydroxyl group, then it would just be propyl alcohol or propanol. Okay. So now here are some common alkyl groups that we'll talk about a lot because they tend to be substituents of larger molecules. So we have methyl, ethyl, and then we get into N-propyl, which is what we talked about in the last slide. It's just a propyl group that attaches to a molecule using one of the end carbons, versus isopropyl, where it attaches to the middle carbon. We have N-butyl, sec-butyl, iso, and tert. So N-butyl, again, is going to attach at the end of the butyl group. Sec-butyl is going to attach at the second carbon, right? So if we were to number these, it'd be 1, 2. So second carbon, sec-butyl. Isobutyl is going to have this configuration where it's attaching to this carbon, and then you have this chain. So even though technically the longest chain is 3 carbons, right? 1, 2, 3, but there are 4 carbons all together. So that was what makes it butyl. But we could call this 2-methyl propane if we wanted to. If we were just looking at this by itself, and this was a CH3 instead of CH2. And then tert-butyl is where it's attaching to this carbon here and has this kind of structure. And the way that I always like to remember tert-butyl is that if you look at this, it kind of makes a T shape, and tert has 2 T's. So I don't know. That's how I always keep track. So these are the different positions or the different carbons that can attach to another molecule for these different alkyl groups. And carbons with these different alkyl groups can be considered primary, secondary, tertiary, or quaternary. And what that means is that if it's a primary carbon, it's only bound to one other carbon, and then the rest are hydrogens or other things. Okay, so this R stands for rest of the molecule, basically. But here we could just easily just write that as C. Okay, secondary carbon is going to be this carbon here, and it's going to be attached to two other carbons. So secondary. Tertiary is going to be this carbon here in the center attached to three. And then, of course, quaternary is a carbon that's attached to four carbons around it. Okay. So, if this was a carbon right here, that was attached to this in the middle, that would be a quaternary carbon because it's got 1, 2, 3, 4 carbons, right? This one, this carbon here, would be a tertiary because it's bound to this carbon, it's bound to this carbon, and it's bound to this carbon. So 3, right? And this one would be secondary because it's got this carbon here to the right and this carbon here to the left. Now, as I mentioned, R just kind of really stands for the rest of the molecule that's not specified. It's a way to write shorthand because, again, scientists are lazy and we don't like to write out all the molecule if we don't have to. So an R just stands for the rest of it and whatever you want to focus on that's attached to that molecule. So an ROH, right, it's going to be some molecule that's bound to a hydroxyl group, and that's going to make it an alcohol. And that R could represent something as simple as just one other carbon. So it would be something like methanol. That R could be 2 carbons for all we care. So ethanol. That R could be something way more complicated. It could be something like cholesterol, which is this molecule right here. Cholesterol is an alcohol. And so that R, we don't really know. We don't have any idea, right? It's just shorthand. It could be something simple. It could be something more complex. Oops. Come on, stop. All right. So let's do it. Let's get into the naming, shall we? I mean, we've done a little bit, but that was rudimentary. Now we're going to talk about things where what if we have like branches, right? This is not just one, this molecule here isn't just one straight chain. Okay. How do we know what to call it? How do we know what the parent is? Well, you got to find the longest chain. And that's going to be what's highlighted. So 1, 2, 3, 4, 5. Right? That's the longest carbon chain we can find. If we did something else, if we did this, it'd be 1, 2, 3, 4. Not as long as 5. Okay. And notice I numbered it this way: 1, 2, 3, 4, 5. Not 1, 2, 3. And I'll get into that later, why we did that direction. But for now, don't worry about that. Find the longest chain, and that's going to be the parent, right? So that's going to be, in this case, 5. So it's going to be pentane. It's not going to be butane here because that's shorter. We don't want that. Okay? So keep that in mind. And let's look at this example. Would this molecule be hexane or a pentane, right? We have, in this, if we counted the carbons that are going horizontally, that's 1, 2, 3, 4, 5, 6, right? And if we count the ones going vertically, that's 1, 2, 3, 4, 5. Okay. So clearly it's got to be a hexane, right? Because 6 is longer than 5. So we would say that this is a hexane, right? Wrong. Because that's neither one of these are the longest chain. In fact, this would be the longest chain right here. 1, 2, 3, 4, 5, 6, 7, 8. And then this is just essentially a branch, right? This is a substituent. And there are 2 carbons, so it's going to be an ethyl alkyl group. All right. So keep that in mind when you're looking at the longest chain. Just don't look linearly, you know, figure out, look at all the contiguous carbons and count up whatever's the longest. And that's going to be your parent. Okay. So, so going back to our pentane, we got to number the carbons beginning at the end that is closest to the first branch point. Okay. So in this case, the longest chain is 1, 2, 3, 4, 5. I'm not sure if you can see my cursor. So 1, 2, 3, 4, 5, right? Or 1, it could be this too. 1, 2, 3, 4, 5. In this case, it doesn't matter if we number this as 1, this carbon is 1, or if we number this carbon as 1, because it's going to end up being the same thing either way. But in this case, we definitely want to number it from this end, though, because one of these carbons is going to be considered a branch. One of these is going to be a methyl group, right? It's going to be on 2. If this is 1 or if this is 1, it doesn't matter because the branch is going to be coming off of this second carbon. If we numbered it this way, 1, 2, 3, 4, 5, or we made this 5 up here. Either way, one of these methyl groups is going to be branching off of the 4th carbon. And we don't want that because 2 is less than 4. 2 would be closer. So that's why we number it in this direction, not in this direction. Okay. So let's go back to our molecule that we were just, my little tricksy molecule that wasn't pentane or hexane, it was octane. Which way? We can number it 2 different ways, right? We can number it like this. 1, 2, 3, 4, 5, 6, 7, 8. Or we can number it from the bottom. 1, 2, 3, 4, 5, 6, 7, 8. But only one of them is the right way for IUPAC, okay? Because if we number it to the left, if we number it this way, now we have this substituent group, this ethyl group, and it's going to be on the 4th carbon, numbering it this direction. But here, now we have this ethyl group that is bound to the 5th carbon. And we don't want that. We want it to be 4 ethyl, not 5 ethyl. So this is wrong, and this is right. So now we've got the longest chain. We've numbered it properly. The next thing that we need to do is name the main chain, okay? Find that longest continuous step or chain of carbons. Number the carbons. From whatever has whatever's closest to the branches. And then you have to figure out, well, how many substituents do we have? Do we have more than one? Do we have two substituents on the same carbon? And what do we do there? Okay, so in this case, we do. In this case, we've determined that we're numbering it left to right, because that makes the carbon that has the two substituents, this methyl group here and this ethyl group here, that's on the third carbon, right? If we instead moved it, numbered it from right to left, this would be 1, 2, 3. This carbon would now become 4. Okay. Well, we don't want to do that. So we number it left to right. And now we have two things, right? Like I said, we have a methyl and an ethyl. And so we're going to use numbers, the number that the carbon is, that those branches are coming off of, to label that. Now, you also need to write these alphabetically. So how do we know? Do we say it's methyl first and then ethyl? No, because E comes before M, so it would be ethyl methyl. And if there are two substituents or two branches, there better be two numbers. So even though these are both on the same carbon, these are both on the third carbon, it should be 3 ethyl, 3 methyl. Okay. So again, going to this example, we have two carbons, ethyl, right? That's an ethyl alkyl group. But the last thing we do is we just write it all out, okay? We use hyphens to separate numbers. And if we had more than one substituent, we'd use commas if there are more than one carbon, which I'll show you an example of later. But when we put all this together, we have our longest chain being 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be, that's our parent. So it's going to be octane. And coming off the fourth carbon is the ethyl group. So we write it 4-ethyl to represent that ethyl being on the fourth carbon, 4-ethyl octane. Now, if we have more than one group, of course, then we have to write that out. So in the first one, we have just one methyl. If we had more than one substituent as the same type, so if we had two methyls on a molecule, it would be dimethyl, or 3 would be tri, etc. Okay, in this case, there's just one methyl group, and it's on the second carbon. And it's on the second carbon because we numbered it that way, because we wanted this branch to be on the lowest carbon possible. We didn't number it from right to left, we numbered it left to right. So it would be 2-methyl pentane. Pentane because the longest chain is made up of 5 carbons. Below, what do we have? We have our longest chain here being 6 carbons, so that's a hexane, right? Because if we numbered it 1, 2, 3, 4, 5, 6, that's also potentially the longest chain, right? And in this is another case where we could number it that way, because it ends up being the same either way. If we number it just straight across, then the third carbon is what's getting the substituents, right? But if we number it this way, it's still going to be the third carbon. So both of those ways, it doesn't matter, right? Both of those ways will work. What you can't do is number it this direction: 1, 2, 3, 4, etc. Because now the carbon with the branch is the fourth carbon. We want to keep those numbers down to a minimum, as low as possible. So we number it this way. We say the third carbon has a methyl group and an ethyl group. So we name it 3-ethyl, 3-methyl hexane. Okay, 3-ethyl because E comes before M. 3-ethyl, 3-methyl hexane because the longest chain is 6 carbons. We wouldn't say 3-ethyl methyl. Okay, remember you have to have, for however many substituents you have, you need to have numbers for that. So we have 2 substituents, an ethyl and a methyl. We need to have 2 numbers, even if it's on the same carbon. How about this one? This one now has 2 methyls, like I had just mentioned before, right? There's a methyl here and a methyl here. And we number it from this carbon here because that allows us to have a carbon that the carbon that has the substituents being 3. Right? If we numbered it this way, it would be 1, 2, 3, 4. It would be the fourth carbon. We don't want that, right? We want it to be the third carbon. So we number it from that direction. And there are 2 carbons or 2 methyl groups on that third carbon. So we would write this as 3,3-dimethylhexane. Okay, which I think I put in here. 3,3-dimethylhexane. Dimethyl because again there are 2 methyl groups, 1, 2, 3 because they're on the third carbon, and hexane because the longest chain is 6. And that's it, basically. I mean, it's going to get more, it gets more complicated when we talk about other functional groups, and we're only talking about alkanes right now, but see if you can come up with a name for this one. Okay, pause it and see if you can figure out what you would name. It's already numbered for you, so we're taking baby steps. How would you name this molecule? All right, so maybe you've paused it and tried it. Well, the longest chain is 6. So 6 is hex, so it's going to be hexane. And coming off of the third carbon here, right? Coming off of this third carbon is a substituent made up of 2 carbons. 2 carbons is ethyl. So we would write this as 2-ethyl, it's all caps, 2-ethyl, and then we just add on the hexane, 2-ethyl hexane. That's it. Now, how about this one? I'm not numbering it for you. I'm not giving you any hints. Pause this, find the longest chain, see what you can come up with. Okay. Now I'm going to pause it too because I got to take a bathroom break. Okay, so let's look and see what the longest chain is. So if we let's just go this direction, right? Just counted those off. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 there. And if we're considering this a branch, though, we want it to be 1, 2, 3, 4, not 1, 2, 3, 4, 5. So we would number it from this direction to make this a 4. Right? If we numbered from this direction, then this would be 5. So that's already off to a bad start. But that's so 8 is the longest chain in that scenario. What if we did, that's clear. What if we did this? Okay, now what do we got? We got 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. So 8 there. And then what other option do we have? We could go this way. Right? And that would be 1, 2, 3, 4, 5, 6, 7. Okay, so no good there. Definitely not doing that. So let's go back to the other options. This one across. And this one down here. Okay, and keep in mind that our parent is obviously 8, so it's going to be an octane. Now let's look, so what that means is that this, no matter what, is going to be our substituent. So if we go, oh wait, no, I guess not. I guess the yellow is our substituent if we're going the blue track. And pink is our substituent if we're going the red track. So let's go the red track. And so pink is our substituent. If we did it that way, it would be 1, 2, 3, 4. So it would be the 4th carbon. If we did the blue track, so going down, we could number it 1, 2, 3, 4. It's still 4. Okay, so in this case, doesn't really matter. Doesn't matter if we go the red track straight across or the blue track going down, because either way, these substituents are made up of 3 carbons. And so it's going to be a propyl group. So let me clear all this stuff off because it's looking messy. So what I'm saying is we can go this way. And this becomes the 4th carbon. And then this becomes a 3-carbon alkyl group, which is propyl. So 4-propyl octane, right? Because it's on the 4th carbon. Alternatively, we could do this. And number it from this direction, 1, 2, 3, and it's still 4. 4th carbon. The longest chain is still 1, 2, 3, 4, 5, 6, 7, 8. And we still have a 3-carbon alkyl group, propyl. All right. So the name would be 4-propyl hexane. 4-propyl hexane. Okay. So with butane, right? We said that that's 4 carbons, meth, eth, prop, but. And if they're in a chain like this, it's N-butane. If they're not in a chain, a straight line chain where, one of the carbon groups comes off the middle carbon, you still have 4. I think I already talked about this. You still have 4 carbons, which technically makes it a butane. But if we're not looking at this as a substituent, but as an actual alkane molecule, then what would it be? It would be technically the longest chain is 3. It doesn't matter if you circle it like that. You can also look at it as being, this is the longest chain, doesn't matter. Either way, this middle carbon has a branch. And coming off that branch is, let's say we write it like this. This is the longest chain, 1, 2, 3, and then there's this methyl group coming off that middle one. So we would actually name that 2-methylpropane because yes, it has 4 carbons, but the longest chain is made up of 3 carbons. And so because that second carbon has a methyl group coming off of it, it's 2-methylpropane. Or, you can shorthand it and just call it methylpropane because, that's the only it can only be on the second carbon to be considered methylpropane, right? If you put this methyl group here or here, then effectively you just have this thing. You have N-butane. So one of the exceptions where you don't have to have the 2 there because it's implied. Okay. All right, so what's next? Just some examples for you to review. Longest chain is going to be these 7 carbons right here. And we number it, draw. We number it right to left because we're saying that this is the substituent. And if we numbered it left to right, that would be 1, 2, 3, 4. That'd be 5 ethyl heptane. But if we number it this way, it's 3 ethyl heptane. Okay. A little bit more complicated. What's the longest chain? It's going to be this right here. And that's 1, 2, 3, 4, 5. So it's pentane. And it has a methyl group here. And it has a methyl group here. And it has a methyl group here. So it has 3 methyl groups. So what's 3? 3 is tri. And where does it have them? Well, it has 2 on the second carbon and 1 on the 4th carbon. So we say 2, 2, 4 trimethylpentane. Again, you have to have enough numbers as you have substituents. We have 3, so we better have 3 numbers. Here, 4-isopropyl heptane. Why heptane? Well, because this is the longest chain, and there are 1, 2, 3, 4, 5, 6, 7 carbons, so it's heptane. 4, 1, 2, 3, 4, 1, 2, 3, 4. It doesn't matter if we number it left to right or right to left in this case, because it's still going to be 4, the 4th carbon. Isopropyl, because it's 3 carbons, so a 3-carbon alkyl is a propyl group, but it's attached to the heptane via the middle carbon, not one of the end carbons. So it's not 4-propyl heptane, it's 4-isopropyl heptane. Okay, I feel a sneeze coming on. Okay, sorry. This is going to be 2,5-dimethyl octane. Why? Simple, because the longest chain is this, and that is 8 carbons. Why 2,5-dimethyl? Well, dimethyl because there are 2 methyl groups, right? And 2,5 because we number it this direction, left to right. We don't number it right to left because then it would be 1, 2, 3, 4, 5, 6, 7, right? It would be 4,7-dimethyl octane, and that's just a larger number than 2,5-dimethyl. So that's why we number it left to right in this particular instance. Oh, here we have octane again, because again, the longest chain is 8 carbons. But in this case, it's 5-methyl-2-ethyl octane. Well, why is it that? Why is it not 2-methyl-5-ethyl? Well, it still applies. We still number it left to right because the first substituent, sorry, in this case, the first substituent would be on the second carbon, as opposed to if we numbered it this way, it would be the 4th carbon, right? And we don't want that. So 2-methyl, 5-ethyl. But we write it as 5-ethyl 2-methyl because we want to alphabetize it, and ethyl, E, comes before methyl, M. So 5-ethyl 2-methyl, and then the longest chain, octane. Okay, so here I've given you the name, and I want you to fill in the blank. Write out the structures for me, okay? And so pause it here, and let's see what we come up with, okay? I'm gonna stop sharing. Okay, so it's 4-ethyl 3,5-dimethyl, no name. And all they've given us is the 9 carbons that make up that longest chain, okay? So in this case, doesn't matter where we number it because we're putting in the substituents where we need to, but you know, they're not already here. So let's just number this 1, 2, 3, 4, 5, 6, 7, 8, 9. Just make it simple. 4-ethyl. So that means there's an ethyl group on the 4th carbon. All right. 1, 2, 3, 4. Let's draw an ethyl. Well, what is an ethyl? It's 2 carbons, right? Like that. 4-ethyl, 3,5-dimethyl. So 2 methyls, one at 3 and one at 5. So we can put a methyl group there. 3, 4, 5. A methyl group there. That's it. All we really have to do is fill in the hydrogens, and you can write all the hydrogens out, or you can do a condensed formula. So this would be CH3, CH2, CH3. This is CH2, CH3, CH3, CH, CH, H, H2, 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 H3. That's kind of hard to see with green. And hopefully you know why some of these are CH3s, CH2s, and CHs. Okay, right? This is a CH3 because this carbon is a primary carbon. It's only bound to one other carbon. So that means it has 3 other places to form bonds, right? CH2, this is a secondary carbon, right? Carbon to the left, carbon to the right. And so it has two other bonds available. So it's going to bind two hydrogens. This CH, what is that? Right, it's a tertiary carbon. It's bound to 1, 2, 3 carbons. So there's only one bond available. So it's just a CH. Same with the next one. Same with the next one. Okay. And that's how we do it. And I think I have step by step. Yeah, I did step by step how to write this out. All right, that brings us to the next one. Try this out. What is the IUPAC name for the following alkanes? So pause it here, see what you come up with. Okay, all right. So let's take the first one. Let me get my drawing thing. Okay, so the longest chain is clearly going to be this thing at the bottom, right? And I am going to number it left to right. Why am I numbering it left to right? Well, because that allows me to have the second carbon with a substituent, right? If we numbered it right to left, it would be 1, 2, 3. But in this case, it's just 1, 2. So that's the way we number it. And then what do we have? We have a methyl group here and a methyl group here. So the largest chain is 7. And so that makes it heptane, right? And then what do we have? We have a methyl at 2. Whoops. We have a methyl at 2. And we have a methyl at 5. And there are 2 methyls. Whoops. So it's 2,5-dimethyl heptane for A. Now for B, let's see here. We can go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so the longest chain is definitely going to be this. And I'm going to number it on this side because I already know that. So if this is my longest chain, that means I have a branch here, right? This line here is a branch. And that's closer to the end than if I numbered it. If I went this way, then I wouldn't get a branch till I got to this one. Okay, and that would be 1, 2, 3, 4, 5, as opposed to 1, 2, 3. All right. So we're going to number it that way. So this becomes 1, 2, 3, 4, 5, 6, 7, 8. What's coming off of our parent or our longest chain? Well, one line here. So that must be a methyl group. One line here. So that's a methyl group. And then this right here. Oh, that is not a methyl group. That is a 1, 2, 3. A 3-carbon alkyl, which is propyl. And where is it binding to the rest of the molecule? On the second carbon. So it's going to be isopropyl because it's bound to the middle carbon, not to one of the ends. And so we put it all together. we get octane because that's our longest chain. So that's our parent, octane. And it looks like we have 3, 4 dimethyl, right? Because we have we have a methyl group at the 3rd carbon and a methyl group at the 4th carbon. So 3,4 dimethyl. And then we have this isopropyl at the 4th carbon as well. Okay, so how would we do that? 4 isopropyl. Now, where do we put that? In this case, we put that right here. Whoops. No. Come on. It's not letting me get back to my text box. Okay, well, let's erase this. Okay. Sorry about that. So I said that octane, not octrane. Octane is our parent. And I said there was a 3,4 dimethyl. And now in this case, we put the 4 isopropyl right there. Now, why do we do that? So we have 3,4 dimethyl. Let's maybe make that. Oh, I can't make it. It's got to be all one color or nothing. It's got to be 3,4 dimethyl 4 isopropyl octane because D for dimethyl comes before I, isopropyl. All right, so if we add prefixes to the prefix, we use those to alphabetize. It's no longer alphabetizing methyl and propyl, although in this case, I guess propyl P comes after M anyway. So either way, propyl is going to come after methyl. So 3,4 dimethyl isopropyl octane. Okay, let's clear this out. Oops. There we go. And this is just walking you through those problems. If my way of describing wasn't very clear, you can look at those slides to review. What are the IUPAC names for these alkanes? Ooh. So, you'll see it in several ways. Like we can provide you molecules written in the condensed structure or the skeletal structure, or in this case, the ball and stick structure. So pause it here and see what you can come up with. Okay, so for A, the longest chain is, I think, going to be this. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, we could also say that this is a 5-carbon chain as well, right? 1, 2, 3, 4, 5. And so if we did that, our branch wouldn't come until the 4th carbon. So that's no good. If we number it using the first one, now that becomes 1, 2, 3, 4, 5. And now we've gone from our branched carbon being 4 to being 2. So we're going to stick with the blue path, making it 1, 2, 3, 4, 5. And so that's going to be pentane, clearly. And what's coming off of the second carbon? Well, 2 methyl groups. Okay, so what we would write for that is two dimethyl, right? Because there are 2 of them. Oh, but there are 2 groups, right? So 2,2-dimethyl. Yeah, I think that's right. 2,2-dimethylpentane. Now, what about B? So let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4. So we could number it like this. 1, 2, 3, 4, 5. We could take a slightly different path and go 1, 2, 3, 4, 5. Okay. Or we could go. Oh yeah, no, I guess that's 1, 2, 3, 4. Those are the 2 longest chains. Those are the 2 options. And again, when you get to this point here, it doesn't really matter which way you go. All right, if we it's getting too busy. If I started at this carbon, this is the second carbon, and that means there's going to be a methyl group coming off of that second carbon. Alternatively, if I started with this carbon, made this 1, it's still the second carbon, and there's still going to be a methyl group coming off that second carbon. Okay, so it doesn't really matter which way we go, if we go up or if we go down. What does matter is the direction that we number it, right? It's important that we number it from this direction here and not this direction, because then our first substituent would be this group coming off of the third carbon instead of the second carbon. Okay, so let's just pick something. Let's just say 1, 2, 3, 4, 5. So pentane, again. Only we have now a methyl group coming off of the second carbon, and then another methyl group and another methyl group coming off of the third carbon right here. So to name that, it would be pentane, because that's our parent. And what we say, we have 2, let's say 2, 3, 3 trimethylpentane, right? 2, not text, right? 2 here, 3, 3, because 2 methyl groups coming off of the third carbon. So 2, 3, 3 trimethyl, because there are 3 methyl groups total. Pentane, because that's our longest chain. Okay, and I mean that's it for naming alkanes. That's what we do, and there's slight changes based on if that alkane happens to be cyclical, meaning if the carbons are bound to each other in a ring, they're all connected somehow. Then we add cyclo to it, so 3 carbons is propyl or propane. But if they're all bound to each other somehow, it becomes cyclopropane, cyclobutane, cyclopentane, hexane, heptane, etc. Okay, so the example here they're giving us, that's a ring of 6 carbons. It's not aromatic because it doesn't have alternating double bonds, so it's not an aromatic functional group. It's just a cyclohexane, and it happens to have a methyl group on it. Okay, so that would be methyl cyclohexane. And we don't need to number it because we're going to use whatever substituent, whatever carbon has the substituent on it, that's what we're going to use to number it. And this only has one substituent, just one methyl group. So it's, again, self-implied that that's going to be 1. But what happens when there is more than 1? Well, then we got to figure out how to number these things. Okay, we got to number these carbons in a way that, again, keeps those numbers as low as possible. And we start with the group that has alphabetical priority. So if we look at the step 2 here, right, it looks like we have an ethyl group here and a methyl group here. E comes before M. So we're going to start with ethyl. That's going to be 1. And we're going to number it counterclockwise because that allows the methyl group to be on the 3rd carbon. If we numbered it starting with this ethyl group and went clockwise, then this would be a 2, 3, 4, and now this would be a 5 carbon. So it would be 1 ethyl, 5 methyl cyclohexane, and that's not what we want, right? We want to keep the numbers down to a bare, well, not to a bare minimum. We want to keep the numbers down as low as we can, okay? So 1 ethyl, 3 methyl cyclohexane. See if you can figure out this one. So pause it here, review, and let's see what you can come up with. Okay, so first of all, let's just look at the ring. How many carbons are in the ring? 1, 2, 3, 4, 5, 6. So we know it's a cyclohexane, like before. And what are the groups coming off? Well, we have let me get my thing. We have this 3 carbons, propyl. It's bound to the middle carbon, so it's isopropyl. And we have a methane here, okay? It's important that you know this is isopropyl because that's going to make this 1 because I comes before M, and this is going to be 3, okay? If this was just propyl, right? If one of the end carbons was bound to this ring, then it would be 1 methyl, 3 propyl, right? LMNOP. But since it's isopropyl, we use I, and that comes before M. So again, we number it counterclockwise so that the methyl group is 3, not 1, 2, 3, 4. So it goes around this way. And so that ends up with a name of 1 isopropyl hyphen 3 methyl cyclohexane. That's the name. Oh, here. Okay. Yeah. So I put in here how that's done. How about this? Draw a line structure. So now you're going to do the opposite. Now you're going to draw the structure for 1,4-dimethyl cyclohexane. Ooh, interesting. Okay. Pause it, see what you can come up with. And then maybe I'll try to draw it on the slide. We'll see. Okay. So 1,4-dimethyl cyclohexane. Let's start with it's always easiest to start with the parent, right? Cyclohexane means that we have a 6 carbon ring. Okay. 1,4-dimethyl. So in this case, it doesn't really matter. We can pick whatever carbon we want to start with. Okay. 1, 2, 3, 4. So 1,4-dimethyl. I feel like I start out okay and then it just gets worse and worse. Now, it doesn't really matter which way you number it, because if you numbered it this way, it'd still be 4. All right, if you went clockwise, 1, 2, 3, 4, counterclockwise, 1, 2, 3, 4. It doesn't matter. You could number this one 1 and make this one 4. Right? Because they are on opposite ends, it makes it it doesn't matter really, but that would be the structure. And I think maybe I also put the answer in here too, a better drawing than what I could come up with. Yeah, here we go. So it looks like this. Okay. Now I'm just going to wrap up with a few more slides. Those were the alkanes, but let's say we had an alcohol, right? So we had something, we still look at the longest chain, but instead of having that E at the end of alkane, we had all. Okay, so these are both the same structures. One is a condensed and one is a skeletal. What's the longest chain? 1, 2, 3. Or would it be 1, 2, 3? Doesn't really matter in this case. We can go either direction, but the longest chain is 3 carbons. And what is coming off of that second carbon? Hydroxyl group. So what would we call that? Well, what else is coming off the second carbon, right? A methyl group. So we could say that this is, the longest group is 3. So propanol, right? Because propane is the alkane version. Propanol is the alcohol version. And it would be 2-methyl 2-propanol. 2-methyl because the methyl group's coming off of the second carbon. 2-propanol because it says that hydroxyl group is also on the second carbon. 2-methyl 2-propanol. Okay. So what would this look like? What happens if we have more than one alcohol group? Well, then we do di or tri or tetra, okay? So for a molecule like this one above here, right? this is the same as this. This is the one on the left is condensed. The one on the right is a skeletal structure, but we would write this as 1,2-ethane diol. Let's break that down. Why is it ethane? Well, because there are only 2 carbons. Because remember, that's not a this here is not a carbon, because there's some other non-carbon thing bound to this. So we're just saying this is a bond between the carbon and that oxygen. So 2 carbons is ethane, right? Eth. And it happens to have a hydroxyl group on one carbon and the other hydroxyl group on the other carbon. So it's 1,2-ethane diol because there are 2. All right. Now, if let's say that this wasn't here. Let's say that it was here. Then that would just be ethane diol. Could you write 1,1-ethane diol? Yeah, but if you just say ethane diol, then again, that's implied because ethane, it can only be on the first or the second carbon. And what about this one on the bottom here? That's interesting. So we have two hydroxyl groups, and then down here we have a methyl group. So what do we do with that? Well, let's start with the ring, right? We have 1, 2, 3, 4, 5. That's a 5-carbon ring, so that would be cyclopentane. And it has 2 hydroxyl groups, so it's cyclopentane diol for 2 of them. And how would we number this? Well, 1, 2, 3, 4. Or we could do 1, 2, 3, 4. In this case, doesn't matter which hydroxyl group you start with, it's going to give you a 1, 2, 4 scenario. Okay. What if we numbered this? 1, 2, 3, 4. And it'd be the same if we went the other way. 1, 2, 3, 4. Now, instead of having a 1, 2, 4, we have a 1, 3, 4. And we don't want that because 1, 2, 4 has overall lower numbers than 1, 3, 4. Okay, so no, not right. We're gonna number it 1, 2, 3, 4. Okay, and so we would write that, we would name this as, what was it? We said it's a cyclopentane. We take off the E, but we don't add all, we add diol because there are 2 of them. Okay, and they're on the 1 and the second, the first and the second carbon. And then what else is there? Well, there's a 4-methyl. Right? Oops. 4-methyl 1,2-cyclopentane diol. Now here's something I wanted to mention. Let's check it. Let's see if that's right. How would I know? Well, there's this great website called MolView. Why isn't that? Why isn't that popping up? Okay. Well, I'll just go there. Oh, maybe that's why. There we go. I still have my annotation on. Okay, so MolView, if you go to this website, it's really cool. It's great. It's close this. Oh, look, caffeine, my favorite molecule. Let's get rid of that. And let's write in, what did I say? 4-methyl 1,2-cyclopropanediol. Let's see what they draw. Failed to load. 4-methyl cyclopropane. What's the problem? That one failed to load too. Interesting. Why? 1-methyl. I look down here. I don't see any option. Well, let's try to draw it. So we have one of these things, right? Our cyclo here, and then there's a, where are my hydroxyl groups? So there's a hydroxyl group, and then that to be a hydroxyl group, it has to be bound to an a hydrogen. Maybe I named it wrong. I don't know. It's always possible. Okay. There it is. Let's clean it up. And what are they calling it? Let's get rid of this stuff. Information card. What's it called? Oh, interesting. 4-methyl cyclopentane 1,2-diol. Huh. Okay. So I'll have to check that out. Why that is? Why it's not 1,2-cyclopentane diol. And I'll get back to you on that. Okay. But still, it gives you kind of an idea of how we go about naming the alcohols. And check out MolView, play around with it, because it can, it's a good way to figure out names of these things. What's going on? Well, what's happening? Oh, that's weird. That's where I was. Okay. Sorry. So I guess they're saying that this should be, what's this error message? Uh-oh. That's strange. Sorry, I'm having Google problems. And hopefully rectify that in just a minute. Or maybe it just doesn't like to go to full screen. Sorry, guys. Bear with me. Hey, hooray. Okay. So check out MolView, play around with it. And then that brings us to these carbonyl groups, right? So if you had an aldehyde, remember an aldehyde is a carbon-oxygen double bond that has a hydrogen attached to it, right? Oops, no. Right here. So this would be an aldehyde, and we would, for instance, if it was propane, it would be propanaldehyde. Okay, that's how we would name the parent. If it's a ketone, remember, ketone is a carbon-oxygen double bond with 2 carbons on either side. And so that would be -one for ketone. So butane would be butanone. And then a carboxylic acid, that is a carbon-oxygen double bond with a hydroxyl group at the end. And so to name that, it would be, we would get rid of the E and it would be oic acid. So carboxylic acid becomes oic acid. So pentane would be pentanoic acid. Okay. A benzene ring, which we'll probably get into later, would be benzoic acid, as an example. Esters and ethers. So for ethers, we replace the "il." So if it's a methyl group that's making up the ether, it would be, instead of 2-methylpropane, it would be 2-methoxy. So we get rid of the "il" and we add oxy. Okay. 2-methoxy propane. And then for esters, it's kind of like carboxylic acid, only instead of it being ic acid, it's 8. So, so for the instance with this molecule here, it's an ester because one of the carbons has a double bond to an oxygen. The other carbon to the other side of that oxygen in the middle does not. And so it would be a methyl butanoate or butanoate. All right. And that's because we have, let's get to my annotations. We have carbon here, 1, 2, 3. Oh, wait, 1, 2, 3, 4. Yeah. So 4 for the butane. And we're not really gonna cover these names much because there's only one other lecture. I want to get into reactions, but just trying to give you an introduction. So if you do end up going into organic chemistry, you'll at least have heard this one other time. Okay. I think this is the last slide. Here are some other things. So if it's the halogens, then it would be, for instance, like if it's an ethane with a chlorine bound to it, it's going to be a chloroethane. So we put that halogen name in front of the alkane. If it's an amine group, it's going to be put at the end. So instead of being chloroethane, it's going to be ethanamine. Okay, so amine. And then if it's a nitrile, having a carbon-nitrogen triple bond, it's going to be the alkane name. So if it's ethane, again in this example, it's ethane nitrile as the naming system. Okay, so yep, that seems like it's the last slide. Whew, man, this seems like a long lecture. I don't know how long I've been out here doing this, but I hope this made sense. If you have any questions about it, come chat with me during lab and lecture time, and we can try and make more sense of this. There'll be some homework this Thursday that will involve this kind of thing, these naming systems. So hopefully it's pretty straightforward, but if not, come see me and we can chat about it. Okay, that's all for today or tonight or whenever it is you're watching this. Take care, and I'll see you next time.